Welcome to the SDK Health Sciences Biochemistry classes. Today our topic is hemoglobin synthesis. Hemoglobin is comprised of two components. One is heme, another is globin. Heme synthesis, approximately 85% of the heme synthesis occurs in erythroid precursor cells in the bone marrow, and the majority of the remainder in the hepatocytes. In the hepatocytes, partly it occurs in the cytoplasm and partly in the mitochondria. So partly in the cytosol and partly in the mitochondria. The globin synthesis took place in ribosomes under the genetic control in cytoplasm. Under the genetic control mean that it is under the control of the DNA, so DNA dependent RNA synthesis and then RNA dependent protein synthesis. This component, DNA dependent RNA synthesis, is known as transcription, whereas this component, RNA dependent protein synthesis, is known as translation. In human, normally they have 8 functional globin chains arranged into duplicate gene clusters. So the 8 functional globin chain, they are arranged in duplicate gene clusters like beta-like clusters and alpha-like clusters. The beta-like clusters, they are comprised of beta, gamma, delta and epsilon globin genes, and they are present on the short arm of chromosome 11. However, the alpha-like clusters comprise of alpha and zeta globin genes, and they are present on the short arm of chromosome 16. So the beta-like clusters on chromosome 11, whereas the alpha-like clusters chromosome 16. Let's see the steps of hemoglobin synthesis. So first of all, we will see I will just give you the brief cycle, reactions, just the names. I'm not going into the detail of all these right now. We will discuss in the next slides. So these are the reactions of heme synthesis. And then at the end of the day, at the end when we add globin in it, so it will synthesize hemoglobin. So it starts, so first of all, just keep in mind the name. So it will start with the succinyl-CoA and glycine. So addition of succinyl-CoA with the glycine with the help of enzyme delta amino levulinic acid synthase enzyme, or ELA synthase, is also known as delta amino levulinate synthase. With this enzyme needs pyridoxal phosphate vitamin B6. So succinyl-CoA condensed with the glycine in the presence of ELA synthase enzyme, it makes amino levulinate, delta amino levulinate. This reaction took place in mitochondria. Once the amino levulinate is synthesized, it comes out from the mitochondria into cytoplasm. Then in the cytoplasm, 2 amino levulinic acid, 2 ELA, they condenses with the help of enzyme ELA dehydratase, which is a copper and zinc containing enzyme. Copper behaves as a cofactor and zinc behaves as a coenzyme. And then this ELA two combination of two ALA converted into a compound which is known as porphobilinogen. Porphobilinogen. Then the four porphobilinogen, they combine together, they condenses with the help of two enzymes. One is uroporphyrinogen 1 synthase and another is uroporphyrinogen 3 co-synthase. And then condensation took place of the four porphobilinogen and they make uroporphyrinogen 3. Uroporphyrinogen 3. Then uroporphyrinogen 3 is decarboxylated with the help of enzyme uroporphyrinogen decarboxylase, and then they are converted into coproporphyrinogen 3. Coproporphyrinogen 3. Then this coproporphyrinogen 3 will enter back into mitochondria, and in the mitochondria this coproporphyrinogen 3 will be acted on by the enzyme coproporphyrinogen oxidase. So oxidation took place and then it will convert into protoporphyrinogen 9. Then this protoporphyrinogen 9 with the help of another oxidase enzyme, protoporphyrinogen oxidase, is converted into protoporphyrin 9. Protoporphyrin 9. Then protoporphyrin 9 with the help of enzyme ferrochelatase or heme synthase is converted into heme, but with the addition of ferrous form of the iron. So protoporphyrin 9 condenses with the ferrous form of the iron. With the help of enzyme heme synthase is converted into heme. Then heme is connected with the globin. Heme is connected in the globin, and then this part heme come out. This part is in the cytoplasm. This part is in the cytoplasm. Heme come out from the mitochondria into the cytoplasm, and then in the cytoplasm it is condenses with the globin, and then it makes hemoglobin. Let me repeat it again for you. Hemoglobin synthesis starts with the concentration of succinyl-CoA with the glycine with the help of enzyme ELA synthase. It's converted into ELA, aminoalbuminate. Then it come out from the mitochondria into the cytoplasm. 2 ELA condenses with the help of enzyme ELA dehydratase and is converted into porphobilinogen. Then porphobilinogen condenses together with the help of enzyme uroporphyrinogen 1 synthase and uroporphyrinogen 3 co-synthase and converted into uroporphyrinogen. Then uroporphyrinogen 3 will be acted by a decarboxylase enzyme and is converted into coproporphyrinogen 3. Then coproporphyrinogen 3 will enter into the mitochondria again, and in the mitochondria it will be acted by the oxidase enzyme, and then it will convert into protoporphyrinogen 9. Then protoporphyrinogen 9 will be acted by the protoporphyrinogen 9 will be acted by oxidase enzyme, protoporphyrinogen oxidase, and is converted into protoporphyrin 9. Then protoporphyrin 9 condenses with the iron molecule, and then under the control of heme synthase of ferrochelatase enzyme is converted into heme. Then heme come out from the mitochondria in the cytoplasm. It condenses with the globin molecule and makes hemoglobin. These are the detailed steps of hemoglobin synthesis. So they are very important and a little bit complex. I will try my level best to make it easy for you. So see here, this is succinyl-CoA, condenses with the glycine. CoA will be removed in the first step. Enzyme is ELA synthase, which is paradoxal phosphate dependent enzyme. And then it will convert into alpha amino beta keto adipate. This is an intermediate compound. Then the same enzyme, ELA synthase enzyme, will cause decarboxylation, and then these combination of the succinyl-CoA and glycine will convert into amino-allulinic acid. These steps took place in mitochondria. These steps took place in mitochondria. This is in mitochondria. Then ALA will come out from the mitochondria into the cytoplasm, and in the cytoplasm, two ALA condenses with each other. Two ALA condenses with each other with the help of enzyme dehydratase. A water molecule will remove. Two water molecule will remove. You can see here, two water molecule will remove here, and then it will make a compound porphobilinogen. Porphobilinogen. In porphobilinogen, it starts with the ring structure, and it has three important things. Number one is, you can see this one, this amino group connected here. Then you have this CH2, then COOH. Then you have this CH2, 2 times CH2, CH2 and COOH, propionic acid. So you have acetic acid and you have propionic acid on one side. So this is acetic acid and this is propionic acid. Then what happened? 4-porphobilinogen will condenses with the help of enzyme uroporphyrinogen 1 and uroporphyrinogen 3, and deamination will took place. 4 amino acid will be removed. 4 amino acid will be removed, and then these 4 rings, they will connect with each other. They will connect with each other. So here you have 4 rings are there. 1, 2, 3, 4. 4 porphobilinogen. See, 4 porphobilinogen. So you have 1 or A, B, C, and D. And they are connected with this CH2 group. See, this CH2 group. This one is CH2 group. They are connected with this CH2 group. The product, this product is known as uroporphyrinogen 3. Uroporphyrinogen 3. Then this uroporphyrinogen, and then you can see here that it has acetate and propionate, acetate and propionate, acetate and propionate, acetate and propionate. So which is here, acetate, acetate and propionate, acetate and propionate. Now this uroporphyrinogen 3 enzyme decarboxylation took place here. Under the control of the uroporphyrinogen decarboxylase, 4 carbon dioxide molecule will be removed. And then when 4 carbon dioxide molecule will be removed, so this carbon dioxide will be removed from the acetyl component. So when you remove carbon dioxide from the acetyl component, the acetyl will convert into methyl group, CH3 group. So all these acetyl group which are present, position 1, position 3, then position 1, 2, 3, 4, this is 5, position 5, and then position 8. So they will be converted into methyl group. So now you have at position 1, at position 3, at position 5, at position 8, you have methyl group, CH3 group, by the removal of the carbon dioxide. And the product name is coproporphyrinogen 3. Coproporphyrinogen 3. Now this coproporphyrinogen 3 will enter into the mitochondria again. And then when it enters into the mitochondria, oxidation took place with the help of enzyme coproporphyrinogen oxidase. There is an oxidative decarboxylation. Molecular oxygen will enter, and then carbon dioxide, 2 of the carbon dioxide molecule will remove. When 2 of the carbon dioxide molecule will remove, so they will remove from propionic acid, and it will remove from position 2 and position 4, So propionic acid will be, when the carbon dioxide is removed from the propionic acid, so the propionic acid will be converted into vinyl group. So now we have, and the product will be protoporphyrinogen 9. So now what we have, after the removal of the 2 carbon dioxide from the propionic acid, then now what we have at position 2 and at position 4, we have vinyl group. See here, this is, we have vinyl group, CH double bond CH2. So now we have this structure. The structure is called protoporphyrinogen 9. What we have in this structure, at position 1, at position 3, at position 5, and at position 8, we have methyl group. At position 2 and at position 4, we have vinyl group. And position 7 and 8 we have. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. So 6 and 7 we have propionic acid. 6th position, this is 6th position, and this is 7th position. We have propionic acid, propionic acid, propionic acid. Now this structure, what will happen next? That protoporphyrin 9, with the help of enzyme oxidase enzyme, 4 hydrogen will be removed. Which hydrogen? These hydrogen, the nitrogen hydrogen, inner ring core hydrogen will be removed. These core hydrogen will be removed. And then when these hydrogen is removed, so this protoporphyrinogen 9 will convert into protoporphyrin 9. Protoporphyrin 9. And then this protoporphyrin 9 will condenses with the iron. Iron will take the central position and is converted into heme. It's converted into heme. Let me explain this again for you guys. So succinyl-CoA condenses with the glycine with the help of enzyme Heme Synthesis, which is paradoxal dependent enzyme. CoA will be removed with the intermediate compound amino-ketoadipic acid. Then with the removal of carbon dioxide by the same enzyme Heme Synthesis, this condensation of succinyl-CoA and glycine will convert into amino-levulinic acid, delta amino-levulinic acid. This reaction took place in mitochondria. Then amino-levulinic acid will come out from the mitochondria and will enter in cytosol. In the cytosol, two ELA molecule, they connect together, and with the help of enzyme amino-levulinate dehydratase, water molecule will be removed, and then these two molecules, the condensation of these two molecules will convert into porphobilinogen. The product will be porphobilinogen. Porphobilinogen have few important points. You can see here that porphobilinogen has this one NH2 group, then it has this one CH2COOH, which is acetic acid group, and then it has this group which is CH2COOH, which is propionic acid group. Now 4 porphobilinogen will connect with each other, and then they will convert it into uroporphyrinogen 3. This reaction is catalyzed by uroporphyrinogen 1 synthase and uroporphyrinogen 3 co-synthase. 4 rings will connect with each other, A, B, C, and D, with these CH2 bridges, with these CH2 bonds, On one end of every ring there is this acetate, on the other end there is propionate. So acetate and propionate, and in the D there is a reversal, that is propionate and acetate. Then this uroporphyrinogen 3 will be decarboxylated. 4 carbon dioxide will be removed, and 4 carbon dioxide will be removed from acetate site, all the acetate sites, and these are position 1, position 3, position 5 and position 8. So 1, 3, 5 and 8, carbon dioxide will be removed. And then once we remove carbon dioxide from acetate, then acetyl group will convert into methyl group or CH3 group. So all these four positions, the product will be copro-porphyrinogen 3. Copro-porphyrinogen 3. And then we will be having position 1, position 3, position 5 and position 8 methyl group. Methyl group. Then copro-porphyrinogen will be decarboxylated. This is oxidative decarboxylation with the help of enzyme copro-porphyrinogen oxidase, and 2 molecules of the carbon dioxide will be removed, and these 2 molecules of the carbon dioxide will be removed from propionic acid. And then the position of the which propionic acid? Position 2 propionic acid and position 4 propionic acid. Position 2 and position 4 propionic acid. So propionic acid will be converted into vinyl group. Vinyl group is CH double bond CH2. They convert into vinyl group. So now we have the product will be protoporphyrinogen 9. And in this product, what we have methyl group at position 1, at position 3, at position 5 and at position 8. And we have vinyl group at position 2 and at position 4. 6 and 7 have the same propionic acid. 6 and 7 has the same propionic acid. And remember, inside every ring there is a nitrogen. There is a nitrogen. And nitrogen is attached to one hydrogen. Nitrogen is attached to in the form of NH. What will happen in the next step, that these 4 hydrogen will be removed with the help of enzyme protoporphyrinogen oxidase, and then this product, this substrate protoporphyrinogen 9 will convert into protoporphyrin 9. The center place is free for iron. Last but not the least, under the enzyme of uracilitase, this iron will come here and then take the center position, and the product is known as heme. Some people pronounce this enzyme ferrochelatase as ferrochelatase. So they are same. This is just a difference between pronunciation. Ferrochelatase. In order to summarize it, so we have 3 components here. One is iron in the ferrous form. Another we have pyrrole ring, and third we have globin molecule. So now let's see. First see the pyrrole ring. So we have glycine from succinyl-CoA, B6, ELA. ELA will come out from porphyrinogen, then porphyrinogen will convert into uroporphyrinogen, then uroporphyrinogen will convert into coproporphyrinogen, then coproporphyrinogen will enter into the mitochondria and convert into protoporphyrin 9. From the top, transferrin brings the iron. Transferrin will come inside, will be engulfed into the cell, then inside the cell the protein is released, transferrin is released, it will return back, transferrin cycle, and iron will be released here. Iron can also come from the ferritin stores in the cell as well. So this iron will condense with the protoporphyrin 9 and it will make heme molecule. This heme molecule will come out from the mitochondria. This come out from the mitochondria. I mean 4 heme molecule, because we have 2 alpha and 2 beta. So 4 heme molecule will come out from the mitochondria and condenses with the globin chain for 2 alpha and 2 beta. And globin is synthesizes from the amino acid under the control of the DNA in ribosomes, and they synthesize 2 alpha and 2 beta chain. So in one side we have amino acid synthesis. On the other side, iron is coming, and inner side, heme is synthesizing, pyrrole protoporphyrin 9 is synthesizing. So protoporphyrin 9 condenses with the heme to make heme molecule. Heme will come out to condenses with the globin and form hemoglobin. I hope it will be clear. If there is any question, any comment, please let me know. So your feedback and comments will help us to improve the our next session. Thank you very much and best of luck.